morally, okay, so open book foliations are morally intersections of open books with surfaces, and these are going to be oriented singular foliations. And the question I answer is whether a given oriented singular foliation is an open book foliation, is coming as an intersection of an open book with a surface. And so the plan is that I first give like an easy example in braid foliations, and then I introduce open books and then open book foliations, and then I give the algorithm. It's yeah, you will see. Sorry. Wait. Yes. All right. So you have R3 with cylindrical coordinates, and you're taking all the half planes in it with a given angle. So these are these HT here. Do you see my hand? Not mine, but the ones on the screen. No. Then is this one? Yes.
I can see the hands. Yeah. Okay.
All right. So yeah. So I'm taking this HT, which are half planes. They intersect all in the z-axis, but that's not going to bother us. So otherwise, they are like somehow disjoint. And then I'm taking a random surface, and I take its intersection with this HT. Okay. So then, for example, for t equals pi, it looks like these two arcs here, these blue arcs here. Okay, and okay, so for somewhere in between pi and 3 pi over 2, there is a moment when it's tangent to the surface, and then it looks like this X.
Oh, Vera, it looks like some of us can't see your hand, or I can't see anything moving at all. Like I see the hand, but it's not moving, and there's a few people in the chat, so I don't know what we should do.
Vera, is it moving on your screen? Like, can you see the little hand cursor moving on your screen?
Yes.
Okay, then it sounds like what probably needs to happen, if you can stop screen share and then start it again, that will probably help.
Stop share.
Yeah.
And then I restart.
Yeah. And try moving your cursor and see. Okay, great. Thank you. So we only saw the title page.
Oh, that's really
so we didn't see any of that.
All right.
Thanks so much, Vera.
Okay. Yeah, this happens. I've been using Zoom and it does happen. Yeah. All right. So, okay. So the plan I already told you, it was also written. And then here are these pictures of the cylindrical coordinates and the half planes, HT. And then I introduce this surface in it, which is just a random surface. And then I'm looking at the intersection. So here is an intersection. This is two arcs. And then when I move forward, it's going to eventually turn into like this X shape. And then the X shape is turning into another two arcs as you move forward. And then when I'm looking at all these intersections, then I'm getting this singular foliation on my surface, which is now torus. So this foliation has singularities. So there is the singularity, for example, on the top, which I'm going to call a node or elliptic point. These are, they just look like that everything is going into or out of it, of the point. And then there is the singularity, which looks like a saddle point or a hyperbolic point. And then there is another type of singularity, which you can see in this picture, is this minima or maxima, which are centers.
Wait, can I suggest to the organizer, is it okay if we just give Vera more time? Because I missed the whole setup, and I think, is it okay? Can we quickly go through the setup again?
Yeah, of course.
So foliations or open book foliations. So in the setup on the next slide, you have a surface in R3, and you're just intersecting it with these
with these half planes, like the half planes with a given angle.
Okay, so just any surface in R3, and you just intersect it with these planes.
Yes.
Okay,
yes.
Thank you.
All right, and then just drew some of the intersections. So this is for t equals pi. And then as I move forward, it's going to look the same for a while. And then at some point, it's going to be tangent. And then it's going to look like an X. And then I move forward, then it's changing. It's changing. And then at the end, I'm drawing all the intersections, all of them. And that gives me a foliation. And then I said that there is this node, which is just the intersection of the surface with the z-axis. There are 4 of them, 1, 2, 3, 4. And then there are hyperbolic points, saddle points. I'm going to use both. Then these are these points when the surface is tangent to the planes. There is 4 of them, 2 you can see and 2 you cannot see because they are in the back. Which is not surprising. I have to have the same number because it's a torus with Euler characteristic 0. And then there is another point which I didn't draw on the torus example. So if you have this, like, that's supposed to be fat. So it looks like that theta, when you look at the theta coordinate, then it has a maxima restricted to the surface. And then these are center points. And then these are all the types of singularities which can occur in a generic embedding of a surface. Okay. And then we can also orient these leaves. So yellow is the top of the surface, orange is the bottom of the surface. Okay, so I'm secretly orienting my surface. And then that gives a co-orientation, and that's what I'm drawing. So the orientation is always somehow pointing away from the braid axis, from the z-axis, for if you are going, if the surface is you see the top of the surface, and if you see the bottom of the surface, then it's pointing inwards. And then this way you can distinguish 2 types of nodes, these 2. So 2 types of nodes, the ones which are like somehow top up, and then the one which are bottom down. And then so these are sources. So the orientation is going outwards, and then the other ones are sinks. And you can also differentiate centers. There are maximums, where the maximum, like yellow maximums, they are somehow counterclockwise, and then there are minimums which are clockwise, that the orientation is clockwise. Okay, it's not going to be important. In a second, I tell you what. And then there is also 2 types of saddles. Somehow you can distinguish whether the normal is pointing in the direction of where the theta coordinate is growing, or it's not. Okay, but I'm not going to distinguish these at this talk. It's very important otherwise. And the reason the centers are not important is because I can get rid of them, and I will get rid of them. So imagine that you have a circle in your foliation. That just means that there is an intersection of these half planes with your surface, which give you a circle. So it looks locally, it looks like that. And then you're taking just a part of the circle, and you push it through with your finger up to through the z-axis. All right, so that's what happens. And then the circle you used to have is going to be cut into 3 pieces, 1, 2, 3. Even the orientation is changing on one side because you go to the other side of the surface. Okay, so and not only that, this one is cut up into pieces, but there were nearby circles, and each of them are going to be like separated into. So you are not only not creating new circles, but you're actually killing an interval verse of circles. And because you can't kill interval verse of circles and using some sort of like compactness argument, you just remove all the circles with finitely many of these like pushing moves. Okay, so that's going to be important, but let's just move forward. Is that so these things have been introduced in the early 1980s, and I'm not talking about this in this talk, but they are like very, very tightly related to contact structures. So this gave the first proof in Banachine stasis that the standard contact structure is tight. Okay, and then later it have been used a lot by Berman and Manasco to give a version of Markov's theorem. You know, these are just like the braid moves you can have without stabilization. So they introduced a more complicated move, but with that you didn't have to change the number of times the braid goes around the axis. So what is that? The winding number of the braid, or okay. And then and this led to a construction of one of the first construction of transversally non-simple knots. The other construction was given by Jonet Nair and Honda, which was one of the lighting talks, that the 2-through cable of the trefoil is also not transversely non-simple. But this one is interesting from Earth's perspective because this one is using braid foliations. And they have used braid foliations for many things, understanding essential surfaces and so on. They did a lot of things. And then recently, they have been like revived. Dinikov and Preslov used them to compute Legendre grid number. So you can there's an explicit algorithm so that for any Legendre knot, you can tell in how big, what is the smallest grid you can put it on. And then they also proved the generalized Jones conjecture using braid foliations. And there is really a lot of other results in these settings. But what I want to talk about is open book foliations. So for that, I'm going to talk about a little bit about open books. So open books are just a pair of a one manifold, and the fibration of the one manifold, of the complement of the one manifold, sorry, so that near the binding, I have to move you guys away. So near the binding, the binding is the one manifold. We have the model, which is exactly what I described earlier in the braid foliation picture. Okay, so we have this HT model there. And in principle, a fibration could look differently. For example, at one time could go multiple times around the binding, and that we don't allow. Those would be called rational open books. So we don't allow those. And there is another naming concept. So each of these pre-images, so at a given time, the fiber of the fibration is called page. Okay, and so we can, you can, whenever you have a fibration, you can think of it as a mapping cylinder. You just take the first return map, and I call that age. And then if I take the mapping cylinder, then I'm almost getting back my three manifold, except the binding appears S1 many times. Okay, and then I'm getting back my three manifold just by killing these S1 many times the binding. I'm just identifying them. Okay, nice cat. And then that's how open books are defined. And they are, sorry. And then here are some examples. I mean, if you want to give explicit examples, you have to have coordinates, and the nicest coordinates you can have is S3 as the unit ball in C2. Then you can take the binding to be Z1 equals 0, and then you can just take Z1, the angle of Z1, basically. Okay, so you take the angle of Z1. Then this one gives you an open book with an unknot being the binding, and with the pages being just disks. And then the return map, first return map, is the only map you can imagine here, which is the identity. Also, if you're taking a slightly more complicated polynomial, Z1, Z2, then you can take its 0 set, then that's going to be a Hopf-Link. And then the function, the fibration is going to be again, Z1, the angle of Z1, Z2. So Z1, Z2 divided by its absolute value. And then you can just check that the pages in this case are going to be annuli. And the not extremely hard computation shows that actually the first written map is a Dehn twist along the central curve of the annuli. Okay, you can take any other polynomial, also in the conjugate. So you get this conjugate one, and then this one is going to give you the annulus, but with the left-handed Dehn twist. All right. Oh, sorry. Yeah. So open book decompositions are useful because any stream manifold has an open book decomposition, and moreover, any two open book decompositions which describe the same stream manifolds are related by an operation, which is a very well understood operation called stabilization. And then also contact stream manifolds can be described by open book, but then you limit the type of stabilization you make to positive stabilizations. It's not going to be relevant what these are. Okay, and then okay, once we have open books, we can take a surface. So this one is supposed to be a sphere, not a disk. Okay, it's a sphere, it's fat, and then I'm trying to draw the intersection of it with the pages of the open book. This is easy. This is one I can draw, and then there's another one I can draw, and the rest I'm just guessing. So you have to understand that at some point it has to be tangent to it, and then oops, sorry, and then you're getting this picture. So it's a sort of a pillowcase. So you have this. Yeah, this is probably not the right word for it, but so you have these four nodal points and two saddles, one in the front and one in the back, which I didn't draw. And then, okay, in principle, I could also have centers, but I'm not going to have centers because I'm getting rid of the circles. And once I get rid of the circles, centers need circles, so they cannot exist. Okay. And then braid folations, no, open book folations have also been used a lot of times. So I think one of the first occurrence I know of is Pavelsku's thesis. And I think she changed her name, but okay. So saying, maybe John knows it. What's her name now? Okay, so she proved Markov's theorem for braids in general open books. It's a very nice characterization of what kind of moves you can do with braids. And then Ito and Kawamura built up like a complete theory of them in a series of papers. They understood over-twistedness in terms of open books. I mean, it was understood beforehand, but they had a very nice like picture for how that looks like. They managed to compute some self-linking numbers for braids, which are transverse to an open book, and so on. And then we just joined in later in this field, and we used these open book folations as boundary conditions for stream manifolds with boundary, and we defined the gluable version of open book. So basically, what you should think of is that you cut a normal open book along a surface which has an open book folation on it. So it's some sort of generic surface, and then you get an open book which has some boundary conditions, so which prints something on the boundary. And because there is this print on the boundary, you can nicely glue them together. And then this gives rise to a gluable invariant in Hegardt-Frey homology as well, because there is a contact invariant in Hegardt-Frey homology for normal closed manifolds, and there is another contact invariant in Hegardt-Frey homology for manifolds with boundary. And that one lives in sutured Frey homology, and this one lives in bordered Frey homology. So this is gluable, like somehow, like in a very natural way. Okay, so yeah, maybe that was enough to understand, to make you understand that I want to understand that it makes sense to understand open book folations. And then in particular, what I'm interested in is that what kind of data I have to give an open book folation. Okay, So, okay, so once again, I assume that there is no circles, so that there is no centers. So what we are getting is we're getting an oriented singular foliation. I'm going to call it FOB, like for open book, which has singularities that are either nodes or saddles. And there is an extra information which is somehow coming from this S1 value of how the open book intersects the page. So if you're looking at the intersection, then as you're going along, then you're like swiping through the surface with your pages, and then eventually you get back to where you were. Okay, and okay, so the first question we are asking is that if someone just gives us an oriented singular foliation on the surface, which has singularities that are also only nodes and saddles, then can this be realized as an embedding into an open book? And then we know already one condition, and this condition just says that like the minimum you need to have for that is that there is an index. You can index the leaves in a way so that whenever you go around one node, which is a sink, which is a source, sorry, then you're going somehow exactly once counterclockwise. No, sorry, yeah, counterclockwise. And when you're going around sink, then you're going exactly once clockwise. Okay, so that's your goal. And then, oops, yes. So then okay. So then I can ask a possibly simpler question: is that can you give an index for the leaves by the circle, so that near each node I have this property that it's either clockwise or counterclockwise, depending on whether it's a source or a sink. And so this looks like a maybe simpler condition, but we prove by a fairly simple construction that these are equivalent. So we have to answer the last question, the second question. All right, so this one is an open book foliation of the sphere, and the time, so on which page you are is shown with the rainbow, with the colors. Okay, sorry for people who are colorblind.
Here, could I ask a question?
Yes.
So when you said this is equivalent, being realizable and being able to put this ordering on, is that true for realizing it in any open book or in some open book?
Some.
Okay.
Some,
But
yes.
if you fixed one, there might be other conditions.
Exactly. Yes.
Okay. Okay. Great. Thanks.
Yes. All right. So the rainbow colors here. So right now we know that this one has to be included in an open book. So let's just try to put it in. So here is, okay, this looks like a random choice of curves, but I mean they are just like, it doesn't matter how you draw them. The only thing which matters is which two points it connects. So look at the pink one, it connects E to B, and it connects F to C and D to A, and then you check that that's exactly what it does on the top as well, on this picture as well. So this is an annulus, and then when you're going forward, then you're somehow like doing the saddle move along this point here. So this is the middle picture, and then this is the orange one you get on the surface. And then as you go forward, you can check that you can just like do the yellow saddle point as you go, and then the blue and the purple one, and eventually you will end up here. Okay, so you will end up in something, and well, that doesn't look very promising because they are different. You started with something and then you ended up with something different, but it's actually okay because we still have some flexibility of how we glue the two points. What is the monodromy? What is the first written map? And then I'm choosing my first written map to be a Dane twist, and then I'm actually getting back to this one. All right. So and then I already know that this one describes S3. So I'm actually getting an open book foliation inside S3. So I'm getting an embedding of S. This one describes explicit an embedding up to isotopy in S3. Okay, up to isotopy, which never changes the intersection with the pages of the open book. All right. So what you have seen is that you don't have to give a time for every single flea. It's enough to give a time for the saddles. Okay, because the rest can be just like continuously extended, and then each node, you remember here, like for example, this node E told me that the yellow saddle and the light blue saddle and the purple saddle had to be in this particular circular order. Okay, so I'm getting some sort of like partial cyclic order given for every single node. So I'm getting like this collection of partial cyclic orders. And then we know that this question of like extending partial cyclic orders into global cyclic orders or total cyclic orders is an NP complete problem in general. It's like one of the, 1977 result. And then, all right, so that's not good. Maybe it's hard, but then we rephrase the problem. I'm not going to talk about that, to finding a maximal acyclic subgraph of an oriented graph, which is associated to this foliation. So the points are the nodes. The points are the saddles, and then somehow the edges tell you the order of the saddles around every node. And that's your acyclic, that's your graph, and you have to find an acyclic subgraph of it. This is also NP complete. This is the one, 1972, this is the moment when people defined what NP complete was. And that's inside in that first paper. And then, okay, so that's also not so good. And then you can also rephrase the problem to finding a minimal embedding, so a minimal genus embedding of this again, the same graph into a surface. In fact, you don't even have to find it. The question if the surface you already have the embedded into is going to give you a minimal surface embedding, and that's also NP complete. So I started to work with some combinatorics people, and we just believe that it's going to be NP complete. And then and we were trying to prove it, and it didn't work. And then we tried to give an algorithm, and it didn't work. And then eventually it did work. So we managed to give an algorithm. And there is a polynomial time algorithm that recognizes whether a given oriented singular foliation is an open book foliation. And then, so that just means that there is a good cyclic order for the saddles, but good just means that it satisfies all those relations around the nodes, or the cyclic relations. And then actually, you can also find the cyclic order in a polynomial time if there is one. So usually there are more than one cyclic order for such a foliation, and the algorithm doesn't seem to find all of them. So it depends on how you run the algorithm. It finds any of them can be found by an algorithm, but I don't know how many times you have to run it. So maybe it's not polynomial, the number of times you have to run the algorithm to get all of them. All right, so, and then finally, I saw this as a combinatorial problem, and then the solution came from topology. So here is one move on the foliation, which I'm calling bypass move, because this is the actual same move as for bypasses. So you have you have two saddles which have two common nodes they are connected to. There is this one parameter family of intervals which are going from one saddle to the other, and then I'm just modifying it locally. Okay, check that all the errors are okay, that these green dots help you to check that the errors are all okay when you are doing this move. And the statement which we are proving is that, okay, so this is two moves. I'm sort of thinking of this move as like somehow left twisting and right twisting of the picture. And then, so unless, you end up having a circle when you're doing this move, then all three of the pictures have a cyclic order if and only if any of the others had. Okay, so this doesn't change the fact whether you have a cyclic order or not. This might not be so surprising. So these moves can, okay, if you already have an open book, then embedding with an open book, that these moves can often be realized as some move of the surface, and then it will of course not change the fact that it's embedded or not embedded. Okay, so this is not so surprising, but it also holds for foliations which are not embedded. Okay, which are not yet embedded. And then, all right, so that's one of the things we prove. And then the other thing we prove is that that by a finite sequence of bypass moves, you can always turn any foliation into one where there is a unique node which is connected to all the saddles. Okay, so this is actually a picture for the entire surface with some of these pairs of these edges being identified. Okay, so your surface is the same, is this picture. Everything is drawn on it. Some of the nodes are drawn multiple times because they get identified at the end. Okay, and then once you have a cyclic order, then you just have to check if that's right. I mean, and then that's easy to do. We can even give like a complete characterization in terms of some permutation. All right, so let's just look at one example. So this is a open-oriented foliation on a torus, and then you're picking one node, and then you notice that this is the order which the saddle points around it has to satisfy. So I'm just noting it, and I know this is the other thing, and then I have 9 nodes, and I draw all of them. So it's not so easy to find an algorithm. So let's just run the algorithm instead of like trying to find one. All right, so I have 9 nodes and 9 saddles. So this guy, so this guy is connected to 7 saddles. So let's just try to increase the number of saddles it is connected to, and that I'm doing with a bypass move here. Okay, so I'm doing a bypass move on the yellow part. I'm changing it like that, and then all you have to notice is that there is another green arc appearing.
Hi, Vera.
So another hyperbolic point got somehow included in the neighbors of your node. And then you do this once more, and then all the hyperbolic points right now are connected to your node. And then now you don't have to guess. If there is an order, then this is the order: first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth. And then you just check that that's not okay, because this node, around this node, this just goes the wrong way. 1, 4, 3, 8 is not part of the cyclic order. So this is.
Hey, Vera.
Yes.
Sorry. The next talk was scheduled at 11:15. I know you started about 5 minutes late, but if you can wrap up in the next.
Yes, that's going to be really fast. Okay. All right. Thank you. All right. So then I'm going to go faster through this one. So you can do the same method here, and then you end up with a cyclic order, which is actually okay. And then you can get back to a cyclic order for the whole thing. And then all right. The funny thing is that even though the bypass move is a local change, the change in the cyclic order is a global one. It looks like here it's a local one because the example is too small, but sometimes it's globally like really messed up. And then all right, and then I just wanted to stop with some open questions. So if you can recognize braid foliations in general, so this was the question John had. If you can recognize if you really embed it into a disk open book, or can you recognize it for embeddings into any other fixed open book, or if you can enumerate all possible embeddings giving the same open book foliation. And some of the questions are answered in some special cases. So this one is answered for S2 and T2, so like torus, all foliations in the torus which can be embedded into a braid as a braid foliation are classified, and then also for braid foliations, this question is answered. You can enumerate, and there is a unique one. Okay, once the order is given, and that's really it. So thanks for your attention.